Welcome back. We're now going to look at this example actually using GLHEPRO. So I've just opened GLHEPRO. These are all the default units. You can, by the way, save your own set of defaults in GLHEPRO. You can put in anything you want, and if you say save as default, the next time you open it'll have those entries. We've done that. Uh, Perhaps unfortunately it means it already comes with default loads, which we would just paste over. So actually, I think the first thing we're do is not start with GLHEPRO, but rather start with the peak load analysis tool. I've already, let's pull this over and fit it in here. Okay, so one thing, I've already put the loads in. And one interesting thing, if you notice here, January 1st, this building's cooling. I thought it seemed a bit odd to me. January is usually not that warm in Stillwater. But then if you look, it goes back into heating. But we have cooling. We can have in an office building here. We can have cooling any time of the year, well, certainly any time of the winter. And let's see. I've already worked this. The units we got from Energy Plus were in watts, and when I totaled them, I divided them by 1,000 to get kilowatts. So the first thing to do would be to compute the peak days. Right, so here's our peak heating day. This sort of morning peak suggests that the thermostat is set to has setback, and so that it's been low at night and then it comes on in the morning. That's something we might want to revisit if we were sizing on heating, but in fact we won't be, so it's not really relevant to our problem. This is a cooling day. You can see at night we have somewhere between 50 and 100 kilowatts of cooling, and then we have this sort of warm up, right, and we get down up to about 300 kilowatts, right, in the late afternoon, and then people go home and it starts to fall off. Okay, the first thing to do would be to pick a set of guesses, and I've already guessed at what we'll bracket that. I've already done this, but we calculate the peak responses. If you look at the heating, a 1 hour peak response would give us a delta T over delta T max of about 78%. It's not quite high enough. 3 hours is a bit too high. 2 hours is pretty close, although we can't quite read it here. So we're going to use a 2 hour peak. And by the way, again, we're using the maximum during the duration. Okay, and then for cooling, because it's sort of a smoother, not such a sharp peak, right? The duration, the difference between an 8 hour duration, 9 hour, and 10 hour duration isn't so high. But roughly the 10 hour and the 9 hour bracket this, so we're going to use a 9 hour. So the last step then would be to get the summary data, which I've already done. So it's totaled all the heating loads for every month, all the cooling loads for every month, found the peak loads for each month. We have to remember what the duration is. It's not 2 and 6, but rather it's 2 and 9, although we don't actually have to enter it there, just have to remember what it is. So we'll get the summary data. Oh, sorry, we've done that. And now we need to copy it here. Now we're ready to come back to GLHEPRO. Now we copied it in kilowatts, so I think I'm going to do most of this example in inch-pound units since the building's in Denver. But to get the loads, then we put this in metric. Just paste the loads. Okay, so probably when I selected, I made some Mistake, although it looks okay. Control C. And we said 2 peak heating hours and 9 peak cooling hours. So let's call this Stillwater Office Demo. Okay, so we can work in SI units or in metric units or English or IP units. So we'll work in IP units for now. The thermal conductivity of the ground that we measured and I say we measured it, we did a rough estimation based on this thermal response test. And we got a thermal conductivity of 2.8 watts per meter K, and that's about 1.62 BTUs per hour per foot degree Fahrenheit. The volumetric capacity that we estimated was if you translate to IP units, it's 37.277. Okay. Now, we need to put in our ground temperature. So we're going to try two things. We'll just see how they come out. So first, we're going to go look for still water. I think if we search on still water, there it is, Stillwater Regional Airport. So we'll use that. It gives us the temperature 62.5. Just for fun, let's see what it would be if we'd chosen tall grass. So the model, or search again. Okay, so it shows a little bit colder, 61.27. I'm going to cancel that. In fact, what we're going to do, right? We measured it as higher than that, so we're going to put in user specified. Okay, we've put in our own temperature, 63.6. Okay, so before we go any further, right, specifically choosing what fluid to use and so on, I'd like to let's just take a look at the loads for a minute. If you look at the maximum, right, it's the maximum cooling loads 1,074, right, and if we did 1,000 tons, so if we took that and divided it by 12, let's say our peak cooling load's about 89.5 tons. So for computing the flow for the moment, I'm going to assume we have 100 tons of equipment and we've decided on 2.5 gallons per minute per ton or 250 gallons per minute. So we'll just put that in here. Also, I think pretty sure we can go back just to pure water. And I know that we're going to be wanting a heat pump entering fluid temperature of around, say, a maximum of 90. If it comes back from the ground at 90, it should go in at 98, 96, something, 97, or maybe even a little bit higher. So let's just choose as our mean temperature 95. We'll calculate the properties. It will not make too much difference. If I remember later, we could check that. But okay, so we need to select the borehole configuration. One borehole is not going to cut it for this field. So we're going to assume that we're going to use some type of large rectangular field. And since we have, let's say, 100 tons of capacity, I'm just going to start with a 10 by 10 rectangle. All right, and we may find that we need more or less. We may find that if we, depending on what we do, we may be able to cut the number of boreholes down significantly. See, right now it's at 15-foot spacing. Let's just try 20. If you have a building like this that's cooling dominated or one that's heating dominated, where you can have temperature buildup over time or temperature drawdown, you'll generally be better off spacing the boreholes further apart. Make this a 5.5-inch borehole. It doesn't really matter what the size is because we're going to find that. We've got parameters for the borehole. We're going to still calculate the borehole thermal resistance. We've got thermal properties for the ground we estimated from our thermal response test and our undisturbed ground temperature. We're using pure water, and by the way, you can ignore the fluid concentration when it's pure water. It never corrects it from if you had antifreeze before. Okay, for the heat pump, I'd like to try using the heat pump that was developed in another lecture. We'll put in the 3-ton corrected one. So select that. Okay, so we've entered the loads. We've entered all the parameters except for the details of the borehole. Right, and this is where we calculate the borehole thermal resistance. And well, let's see. We've made an estimate of what our borehole thermal resistance is. We'll start, I think, with regular grout. The grout in the borehole that we tested before was a type of thermally enhanced grout. But we'll start with a grout that we, sort of typical bentonite grout, and then we'll work from there. Okay, so first let's go ahead and set the pipe dimensions. So we'll put in try 3/4 inch SDR11. Now, we should in the end check the pressure drop to make sure it's not too high. But for now, I think this should be okay. So we've got that. And we're going to choose the B spacing, right? And this, again, in my own experience, this corresponds pretty well to what we get if we just put the U-tube downhole in an uncontrolled fashion, right? It doesn't, the tubes don't go and touch each other the whole way down, and they don't go out and stay against the side opposite each other. Okay, the volume flow rate, is based on the number of boreholes. So we have 100 boreholes, and the flow we specified 250 gallons per minute. And of course, if we cut down the number of boreholes, then we'll get a higher flow per borehole. We have grout in the borehole, not groundwater. And this 0.43, this would be a sort of typical bentonite clay. I think typical values are 0.38 to 0.43 BTUs per hour per foot degree Fahrenheit. And we'll leave in the short circuiting effect, so they won't have much of an effect if we stick to, say, 250 feet deep. Okay, so we calculate the borehole resistance. Okay, the Reynolds number is 12,700, so we're well into the turbulent region. We're calculating the water properties at 95 Fahrenheit. And we get a borehole resistance of about 0.4176. This is higher than what we measured. I'd have to go back and look, but right, this is about twice as high as what we measured. So, okay, so we've calculated the borehole resistance. That's probably a good place to take a break. So we'll just stop there.